Good. Okay, today I'm starting to talk of infiltration models, and basically I just would like to introduce the processes in which we are talking about, because infiltration, we mentioned it before, but didn't treat it explicitly. What is infiltration? Basically, it is the process that happens when the rain reaches the soil. So usually when you have some precipitation over a soil layer, you have some precipitation, then when the rain reaches the soil, usually we assume that there is a separation. In classical hydrology, we assume that there is a separation in two components of rainfall. One component is called infiltration, and basically penetrates into the soil, and another component is the surface runoff, which basically is water that flows over the soil. And of course, this is an ideal schematization. You can imagine that if the ground is impervious, which means not permeable, then you can easily understand that you don't have separation. You just have water flowing over the soil, like over the roof of an house. When it rains, you see water flowing like a sheet over the roof. And the same happens when it rains over a rocky surface, so you don't have any filtration. On the other hand, in very permeable soils, you may have the opposite, no separation, because all the rain infiltrates. And between these two extremes, we have situations that are, let's say, in the middle. And so the usual schematization that is adopted in classical hydrology is reported here. And this kind of schematization is not unanimously accepted, because, you know, it's not clear what happens when rain reaches the ground. Some people think that, some researchers think that indeed we have a separation in two components. Others say that in many soils, especially the soils where permeability is quite pronounced, you have no separation because all the water infiltrates. And then it's underground that you have a kind of separation, part of water that flows downstream very close to the ground surface, and part of water instead infiltrates in the deep of the soil. And therefore it's in the underground that you have a separation in two components, let's say a fast flow and a low flow. And this second formulation was suggested because, you know, indeed, if you go over the ground, and if you go over an islote when it rains, even when it rains very heavily, you don't see water flowing over the soil typically. You see water flowing over the soil only when permeability is really reduced. In a normal situation, you don't see any water flowing over the soil, but still you see that the water in the river, the discharge in the river increases rapidly. So the hypothesis is that there is a fast flow which is just underground. So these are two different situations, and in any case, there are two different theories, two different, let's say, assumptions regarding runoff formation, because it's clear that whatever it happens, at a certain point you have water that from either because it flows over the ground or either because it flows in the immediate underground reaches the river. And the fact that you have part of rainfall, this phenomenon, which causes that part of rainfall increases the runoff of the river immediately, it's called surface runoff formation. So this process, underlying the fact that when it rains you have a fast increase of runoff in the river, it's called runoff formation. And there are basically two assumptions regarding runoff formation. there is one first assumption which corresponds to this schematization that you see here. So people, some researchers assume that the runoff is formed because part of the rainfall flows over the ground. So this is the first mechanism, which basically assumes that you have to need a separation into components. And this is called the Horton mechanism. A second assumption is that all the water infiltrates, and then when the soil gets saturated, the water emerges. So basically you have a water flow in the underground, and then when this water flow reaches a saturated zone, saturated means that all the soil storage capacity of water is filled up, then you have emergence of water. Water comes at the soil surface. And this is called the Daniel mechanism. So again, two principles, two different schemes. One is the separation of rainfall, which corresponds to the scheme that I have depicted here. The other one is all the water infiltrates. As I said, we assume that there is a flow that takes place just underground, and then when the soil gets saturated, you have that water emerges. And these two names, Hortonian and Daniel, they are derived from a family name of two researchers. Robert Horton was one of the first experimental hydrologists. He lived around 1930-1940 in the United States, and he set up an experimental watershed in his garden and made a lot of observations. And then he postulated that the runoff formation in his garden was originated by this kind of subdivision. And probably the reason is that the permeability in his garden was reduced. On the other hand, Thomas Gunn is an hydrologist that is still living, and he postulated and made reference especially to the UK, where you have soils that are highly permeable and not steep. He postulated that there is no separation of rainfall. All the rainfall infiltrates, and then when the soil gets saturated, as I said, you have emergence of water, let's say water emerging. And what actually happens in practice is a mix of these two mechanisms. If you have reduced permeability, you can assume that the Hortonian mechanism prevails. If you have instead a very significant permeability, very high permeability, then you can assume that the Daniel mechanism prevails. And let me show you a couple of pictures, animated pictures, that better explain what may happen. Let me see. So what is this? This is an animated picture, and this is a representation of the Daniel mechanism. It's a continuous representation, so you can just look for a while, and you have rainfall, infiltration, the water table that reaches the ground, and then you have runoff production here. So again, starting from a dry situation, you have rainfall, and then all the rainfall infiltrates, and then by infiltration you increase the level of the water table until the water table reaches the ground, and then here you have runoff formation. This is an animated picture that I did myself. I'm very proud of it. So you should say that it's very nice. And let me now show the other one, the Hortonian. Here you have similar situation, you have rainfall, but you have the separation. You see overrun flow and infiltration, and therefore you have the water table that increases, but possibly doesn't reach the ground, but still you have a formation of runoff at the soil surface. So in the first case, you have a connection between the water table and the surface runoff. In the second case, which is this case, you see that the water table is not necessarily connected. Fine. let's go back to our PowerPoint. So this is the process, infiltration. Now, how is infiltration considered in the models that we did so far? We treated the time area method, the linear reservoir, and the IMOD model. So, in the time area method and linear reservoir, infiltration is taken into account through the runoff coefficient. Basically, in the time area method, if you remember, we assumed that the contribution to the formation of the river discharge is given by only a fraction of rainfall, which is the total rainfall multiplied by the runoff coefficient. So we introduce a runoff coefficient. What is the runoff coefficient? It's a multiplier lower than 1 that decreases the amount of rainfall because it's used to compute what is called the net rainfall. So the part of rainfall that contributes to the river discharge. So basically it's a very simplified way of subtracting infiltration from the total amount of precipitation. So it's a very simplified way of taking into account the infiltration process, because of course this infiltrated water may reach back the river, but in some cases may not. And therefore, basically, in the ideal situation where you have all the water that reaches back the river, then the runoff coefficient is 1. But in the situation in which you have some infiltrated rainfall that doesn't reach back the river because for deep percolation or because it reaches back the river after a very long time, then we introduce the runoff coefficient. Again, it's a very simplified and conceptual way of representing infiltration. In the IMOD model instead, infiltration is considered because you compute the soil storage. So you may remember that in the IMOD model you have the soil storage in the watershed that increases. So this is some water that is stored in the watershed and not immediately given back to the river. And therefore, basically, from the total rainfall you subtract something, which is the storage. And this storage may not go back to the river, even after a long time, because you subtract the evapotranspiration. And therefore, the combination of water storage plus evapotranspiration means that the soil keeps some water, and then this water is evapotranspired. This is another, if you want, more detailed but still conceptual way of taking infiltration into account. Of course, people realized that, especially in some cases, it's very important to model infiltration in a more refined way. And therefore, people developed a lot of infiltration models, which more or less try to describe the process with more detail. And therefore, these infiltration models are subsequently incorporated in the body of a rainfall runoff model. So instead of using the runoff coefficient, you compute infiltration in some way, and you determine a kind of time-varying runoff coefficient to introduce, for instance, into the time area method. And therefore, basically, I told you that there are many and many rainfall models. One of the main issues for which they differ is modeling infiltration. Now, what I would like to do now in the next hour, and maybe on next Monday, is to explain to you some more refined model for infiltration modeling. But I won't go into much details. I will just deal with simple models, more complicated than just introducing a runoff coefficient, but still simple models, and because I don't want really to spend much time on this, because otherwise it will be too detailed if compared with the other issues that we are dealing with. So basically, here you can see what I already explained. Basically, infiltration modeling is embedded in some models like IMOD, Ortonian versus Vernier approaches, and here you can see a first example of some very simple models for taking infiltration into account. And let me just explain briefly what I mean with these two models. And the first model, you see fixed threshold and percentage model. So let me start with the second. the percentage model. What is the percentage model? The percentage model assumes that when you have a hyetograph, precipitation versus time, precipitation intensity, let's suppose that the hyetograph is observed at hourly time scale. So you have 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. And you have this kind of hyetograph, for instance. This is an example of a hyetograph. The percentage model assumes, and this is gross rainfall, which means the rainfall that you observe, the total amount of rainfall, because we distinguish between gross rainfall and the net rainfall. Net rainfall is the part of the gross rainfall that contributes to river discharge formation. So the percentage model assumes that a fixed percentage of rainfall is lost, doesn't contribute to the formation of the river discharge. So let's suppose that this percentage is 50%. Then you subtract from the hyetograph the lower half. And please note, this is nothing else that introduces a runoff coefficient. The runoff coefficient, if you take a runoff coefficient of 0.5 within the time area method, you obtain the same result. So the percentage model is nothing else than introducing a runoff coefficient. There is instead another model, which is the fixed threshold, which assumes that we can fix a threshold like this one, such that the part of the hydrograph that is below this threshold doesn't exist, doesn't contribute to the surface runoff. This is the fixed threshold model. These are very simple models and conceptual. Okay, now let's introduce the Oracle model, which is by far the most classical method for representing infiltration. We have a picture here, but let me make a sketch also on the blackboard. The Orton model. So let's say that we indicate infiltration in terms of intensity, meaning water depth per unit time with the symbol Ft. This is infiltration. And the infiltration is given by the sum of an asymptotic term plus an exponentially decreasing term. Here is so if we draw a graph, which is a replication of the graph that you see on the screen. Then you can identify on the graph an asymptotic term Fc. And then you can identify, again on the graph, a starting value f0. So you start from an initial value of infiltration, which is f0, which takes place when the soil is dry. And then it starts raining, the soil becomes wet, and therefore the infiltration rate decreases. And it tends asymptotically to the value Fc. You see here that for increasing time, you get to Fc, because if you have for time that tends to infinity, the second term vanishes, and therefore you get that Ft is equal to Fc. While at the beginning, for time equal to 0, you have that infiltration is just equal to Fc plus F0 minus Fc, which means F0. So this relationship here gives to you exactly this situation, which is the same that you can see here, even if here it's a bit more complicated. So I prefer that you look at that graph, because this is a bit more complicated, because I will explain you why it is more complicated in 5 minutes. So basically, the Orton method, proposed by Robert Orton again, assumes that when the soil gets saturated, you have an asymptotical value of infiltration, which may be, of course, different. It can be 0, it can be greater than 0, depending on the soil. And from an initial value, you convert to the asymptotic value through an exponentially decreasing function. Okay. Of course, here you have some parameters, and the most relevant parameter is the scale. The K value dictates the rapidity with which you converge to the asymptotic value. And the smaller K, the faster the convergence to the asymptotic value. And of course, K depends on the soil properties and should be estimated. But there are other parameters here which are not so evident, but indeed they are in place. And there are other two parameters, which are Fc and F0, which still depend on the soil properties and usually are estimated. So basically what people do is to use literature suggestions for guessing the values of these parameters. But if it's possible, people try also to calibrate these parameters by using observations. And especially in an experimental watershed, it's possible to get observations. Because in experimental watershed, experimental means that you have the opportunity to monitor everything. So in experimental watershed, you can observe rainfall and you can observe also the river flow. And therefore, by comparing rainfall with the river flow, you can get an idea of these parameter values, and this is what Robert Orton actually did. Okay. But there is an underlying assumption which is not really so explicit in the Orton model. The underlying assumption is that rainfall intensity is always greater than infiltration intensity. Because otherwise it's clear that if you have rainfall which is less than F0, you can get a value of infiltration that is greater than rainfall. So if your rainfall intensity is here, so let's put here your P0. If you have P0, which is lower than F0, of course you will have an infiltration which is equal to P0 and not greater, because you cannot, again, have more infiltration than rainfall. And therefore there is an underlying assumption in the Orton method, which is that rainfall is always greater than this infiltration curve. Otherwise, the infiltration curve is not valid. And therefore people, started to think to what happens if rainfall is lower than the infiltration curve, than the infiltration intensity. And therefore these people proposed to modify the infiltration curve accordingly to what is depicted there. And now I'm trying to explain on the blackboard what they proposed. Now let me refer to the case where I have rainfall observed at hourly time scale, just to make an example of reference. So let me put 1 here, 2, 3, 4. And let's suppose that here we can represent infiltration, Ft, but also rainfall intensity, Pt, against time. And let's suppose that rainfall is constant, like this. In the sketch that you see on the screen, rainfall is this curve here, which is not constant, but it doesn't change anything. You can assume that it's constant or not. And let's suppose that the infiltration curve is given by F0 and Fc. So the infiltration curve, basically, I look if there is a curve, so say not. So let's try to. Infiltration curve is given by something like that. Okay. So what can we do? Now let's refer to the first hour and what happens at the end of the first hour. Of course, you have an infiltration which is given by this volume here. Because rainfall is always lower than the infiltration curve. Fine. And therefore you have an infiltration that is given again by this volume. Why this volume? Because here you have an intensity of precipitation multiplied by time, you get a total amount, length is the unit of measure of infiltration. Okay. Now, the idea is, given that infiltration is much lower of what is given by the infiltration curve, why it is much lower? Be careful, because if I assumed that the infiltration was given by the infiltration curve, then infiltration would be all this volume here. You see, I have an overestimation which is given by this portion of area below the infiltration curve and above the rainfall curve. So this area, which is comprised between the infiltration curve on the top and the rainfall curve on the bottom, is overestimation. So basically, I cannot accept this infiltration curve in this form. I cannot say that infiltration is given by this infiltration curve, because I get an overestimation. So the idea is, let's shift the infiltration curve on the right in order to make the two areas the same amount. So basically, let's refer to the amount here below the precipitation curve, and let me move the Orton curve in this way. So that if I start from here and I stop here and I compute this area, this area is identical to this area here. So at the end of the first hour, I can say that the actual infiltration is given by the shift infiltration curve. Fine. I think that so far so good. I think the concept is quite clear. And what is the purpose? The purpose is, at the beginning of the second hour, to be able to draw a modified infiltration curve, which should be, of course, above the old infiltration curve. Why above? Because my actual infiltration was lower than the infiltration given by the old curve. So if I want to update after 1 hour the infiltration curve, I should update a curve that is above the old one. Is this clear? And the concept is to make, at the end of the first hour, a balance between actual infiltration and infiltration that will be given by the shift infiltration curve. And this is what you see here. You see I1, which is a different symbol for precipitation in the first hour, times the time step, should be equal to the integral of the new infiltration curve between a new time origin, tau, and the end of the first time step. Is exactly the same thing that you can see here. So you compute basically, for varying tau, you compute this integral between tau, which is comprised between 0 and 1 in our case. So you compute the integral between tau and 1 for varying tau of the infiltration curve, and you find the tau value, which makes the integral identical to I1 times the time step. Now let's move to the second step. End of second hour. And here you already see something a bit different. If you move to the end of the second hour, you see that accordingly to the previous infiltration curve, you would expect that at a certain point you get to a situation where rainfall is greater than infiltration. Actually, this is not the case because I shifted the curve. So I can repeat the same reasoning. At the end of the second hour, I have my infiltration, which is given by this rectangle here. This is my infiltration. And then what I'm expected to do is to move again the curve, for instance here. By equating what? Again, this area with this area. Good. And so forth. Just pay attention to one fact, that if you try to apply this procedure in practice, some iteration may be needed. Iteration because, you know, in this case it was very simple, because I had always precipitation below the infiltration curve. But if, for instance, you look at a situation like this, and you have an infiltration curve, for instance, like this, and you have precipitation like this. So basically, you know, it's not clear what to do. So this is Fz, this is Fz. It's not clear what to do. Because, you know, if you assume that all this area infiltrates, you are not sure about that. It could be that all this area infiltrates, but you are not sure, because at a certain point you get against the infiltration curve. Of course, this infiltration curve should be shifted a bit, because during this period you have this overestimation given by this triangle here. And therefore, you know, this curve, it's true that it should be shifted, but even if you shift it, it's not sure that you can get to a situation in which you have the infiltration that is given by the total amount of rainfall. And therefore, what you should do is an iteration. Like, I assume that all rainfall infiltrates, and then I shift the curve. But then, what do I see? I see that it's not true.